What's up, everybody? Welcome to lecture 23. Lecture 23, right? Yeah, I think it's lecture 23. Welcome to lecture 23. Today we're going to go over section 4.2 and maybe get into a little bit of 4.3. But to start off with, let's look at what we ended with last class. So the first one we've got is the fundamental theorem of algebra, which basically just says that, if you got this polynomial, call it f of x, whatever, and it's of degree n, where n is greater than 0, then you're going to have at least one 0 in the complex number system. So what's 0? Well, that's a very good question. I'm happy you asked. A 0 is just some value of x that when you put it into that, your function comes out to be 0. The end. It's called the linear factorization theorem. Basic idea of it is to say, so you've got this polynomial, f of x, it's of degree n, where degree n is greater than 0, then you have exactly n linear factors for that function. Okay, so what does that mean? That means here, for this function here, let's call this f of x, right? For that function there, you're going to have exactly 12 factors. Why is that? Because the degree of your polynomial here is 12. The degree is the power on your highest term. It's the highest power in your polynomial. All right, so in this first example, we want to put to use those two theorems. Particularly, we want to put to use the linear factorization theorem. What we've got are two different questions. The first question we've got involves x cubed plus 4x equal to 0, and the second one is x squared equal to 0. What we want to do is we want to find the degree of these polynomials, the number of linear factors that these polynomials have, and then we want to solve these. Okay, so to find the degree, we want to find really just the highest power of this beast, this monster up here. Well, in this first problem, the degree is going to be 3. And the number of linear factors, well, according to the linear factorization theorem, it's just going to be 3 as well. So how are we going to solve this? That's the next question, right? Or the next part of this question. Well, the first thing we might do is say, well, we pull out an x. So let me do that. Let me factor out that x. When we do that, we're going to have x times x squared plus 4. This whole thing equal to 0. Well, from this I can see that one of my solutions will be whenever x is equal to 0, right? Because if x is equal to 0, then we have 0 times whatever this will be inside, looks like 4. Well, 0 times 4, it's still 0. So that's one solution. Now we have to figure out when this thing is equal to 0. So we're going to have to solve x squared plus 4 equal to 0 now, right? Well, when is that equal to 0? I don't know. Not looking at this, not right away anyhow. But I know a way to find out. We can apply everybody's favorite formula, the quadratic formula. I know, everybody's cheering at this, right? Because everybody loves the quadratic formula. Whoever just groaned, you failed. Okay, I can't actually do that, but it would be cool if I could. So now, to solve the rest of this problem, we're going to apply the quadratic formula to this. The quadratic formula says that the solutions to ax squared plus bx plus c equal to 0, the solution to this equation, well, it's going to be x equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. That's a quadratic formula, right? Well, in our problem, we don't have a b, it's just 0, which makes this a lot easier. Because what that means now, since a is equal to 1, right? 1 times x squared is x squared. B is equal to 0, and c is equal to 4. That's what this 4 is here, right? This is our c, based on this original equation. Well, because of that, all we're going to be left with is x is equal to plus or minus the square root of 4, of my mistake, negative 4 times 1 times 4, all of this divided by 2a, so 2 times 1. Well, this, once we reduce all of this, this all comes out to be plus or minus the square root of negative 16 over 2. Well, that becomes then plus or minus I times 4 over 2. So x here, the other solutions to this will be x equal to 0. Once we reduce this fraction down, we're going to get I2 and negative I2. So x is equal to 0, imaginary 2, and negative imaginary 2. Really, this is kind of straightforward, right? All we're doing is trying to get these degrees down so that we can apply the quadratic formula if we need to. We don't always need to. What I mean by that is we're trying to factor out terms and get it to the smallest number of terms we can possibly get it to. Well, once we get it to here, something nifty happens. Nifty, something special happens here. We can now rewrite this equation in terms of these roots, these zeros. We can now rewrite it as this thing is equal to x times x plus I2 times x minus I2. Now, why is that? Well, look what happens. When x is equal to imaginary 2, this term goes to 0, so all this has to be 0. When x is equal to I2, or I mean, my mistake, negative I2, this term goes to 0. So all of this has to go to 0. And when x is equal to 0, this factor goes to 0. So all of it has to go to 0. And my mistake, I keep saying term, and I need to say factor here. It's admittedly a bad habit of mine. But these are each factors of our polynomial. But check it out. Like I said, these are factors, right? And we said we'd have 3 factors. Well, we've got 3 factors here. Huh, that's nifty, that's handy. That's convenient because that means the linear factorization theorem tells us something about the number of zeros we might expect. Tells us something about them. Having said that, let's look at this next problem. X squared. X squared is equal to 0. Well, the degree is obviously 2. The number of linear factors is obviously 2. 2, 2, and we know x squared equal to 0 only happens when x is equal to 0. Well, this thing is not equal to x, is it? No, not at all. But it is equal to, let me write this in a different color. It is equal to x minus 0 times x minus 0. So we can still break this down into 2 different factors, but they're not unique. Now, what does this tell us? What does this mean? Well, what this means is if the number of roots that your polynomial has is less than the number of linear factors, then one of them is going to repeat. One of those roots has to repeat at least once. And because of that, you have this discrepancy, right? What this is telling us then is that the number of linear factors is the most number of zeros you'll have to these problems. It's a bounding term. It's the most number you could possibly get. So what does this mean? What am I saying here? What I'm saying here is that for any polynomial, when you're trying to find all the roots, if you find more roots than the number of linear factors, you did something wrong. If you find less, well, might be worth checking, or it means that when you go to write out the linear factors, one of those linear factors, at least one of them, needs to have a power on it. So notice we can rewrite this now here as x minus 0 squared, but x minus 0, that's x, same thing, right? Exact same thing. So, having said that, let's move on. Let's look some more into this quadratic formula. There's some special properties I want us to check out. All right, so just some details about everybody's favorite formula, the quadratic formula. For the purposes of our class, there's one particular part of it that we're going to be interested in. It's this bit underneath the radical. We call it the discriminant. And what the discriminant tells us is whether we're going to have complex solutions, real solutions, and if we have real solutions, are they going to be repeated? And the way it tells us that is just by what it's equal to. If whatever the discriminant is equal to is less than 0, we're going to have two complex solutions. If whatever the discriminant is equal to is 0, so if the discriminant is equal to 0 is what I should say, and then we have one repeated real solution. And if the discriminant is greater than 0, we're going to have two different real solutions. All right. Now let's look back at the discriminant and see if we can kind of fish out why this is. If the discriminant is less than 0, then we're going to have a negative value underneath the radical, right? And if we have a negative value under the radical, then we're going to have an imaginary number. And if we have an imaginary number, it's going to be a complex solution, right? Yeah. If it's equal to 0, then check it out. This whole top bit disappears. Everything under the radical goes away. We're just left with negative b divided by 2a. That's just one number. But if it's not equal to 0 and it's positive, then we have negative b plus whatever's underneath the radical, and negative b minus whatever's underneath the radical. Then obviously we divide by 2a. So the reason why we get these just has to do with the mechanics of algebra, right? The way this thing is working. Because we've got this plus or minus. Whenever our determinant is not equal to 0, we're going to get two different solutions. Whenever our determinant is less than 0, we're going to get complex solutions. Whenever it's greater than 0, we're going to get real solutions. Whenever it is 0, we're going to get one repeated solution. So let's use this. Let's check it out a little bit. Let's see an example. So for these two different examples, we're going to look at them in slightly different ways. This first one, we're actually going to solve. And the second one, we're just going to try to figure out what to expect from our solution. All right. So looking at this first example, how are we going to solve that? What are we going to do here? That's not a squared, so I can't apply the quadratic formula, right? Like x squared here, that doesn't work. So what are we going to do? Well, one thing we can do is apply a substitution. So we're going to start off by just rewriting everything. X to the 4th minus 1 is equal to 0. And we're going to say, let's make a substitution. Let's imagine for a second that u is equal to x squared. Then that means x to the 4th minus 1, that's equal to u squared minus 1. This means x to the 4th minus 1 is equal to u squared minus 1. Well, I can break this up. I can break u squared minus 1 up into two different factors. This is going to be the first factor, u minus 1. The second factor, u plus 1. Now let's put x squared back in here. When we put x squared back in, we get x squared minus 1 and x squared plus 1. Well, this first factor, I see that I can break it up right away. I can break it up into x minus 1 times x plus 1, and I still have no clue what x squared plus 1 factors out to be. But all of this is equal to 0. And if neither one of these are 0, then x squared plus 1 has to be 0. So I can apply the quadratic formula. So let's do that really quick. We've got x squared plus 1 is equal to 0. We want to apply the quadratic formula. Well, we know the quadratic formula says x is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. We know here that b is equal to 0, c is equal to 1, and we know that a is equal to 1. So we can go ahead and apply now the quadratic formula. We can just put those through, right? What we're going to find is that x is equal to the square root of negative 4 over 2. Well, negative 4, the square root of that, it's just going to be 2i, right? Almost, because I had a typo up here, plus or minus. I just realized it as I was saying it. So x is equal to plus or minus the square root of negative 4, all of that divided by 2. Well, that means this whole monster is going to be equal to plus or minus imaginary 2. My mistake, just imaginary 1. Or just the imaginary number. So I claim this helps us, but how does it help us? Well, it goes back to what I was talking about at the very beginning. Linear factorization theorem. We can take and factor out our polynomial using the zeros of our polynomial. We can rewrite our polynomial now, this part of it, as all of this tells us then that x squared plus 1 is equal to x plus I times x minus I. This is equal to 0. Now, I'm just going to rewrite it like that. How did I get that? I'll explain that in just a second. But for right now, this means that we can now rewrite all of this as x minus 1 times x plus 1 times x minus I times x plus I, all equal to 0. Okay, so what this means then is that the solution to our first problem has to be x equal to 1, x equal to negative 1, x equal to I, and x equal to negative I. Now I said a second ago that linear factorization theorem lets us solve this. And it does. Because what linear factorization theorem really tells us, what's at its heart, is that, let's say you've got some crazy polynomial. It's equal to whatever. You can always factor it out to fit the form a sub n times x minus c1 times x minus C2 times, and this goes on forever until we get to x minus Cn. Okay, what is this? What's n? N is the degree of your polynomial. So if you're at polynomials of only 1 degree, you stop right here. It is just this part, if your polynomial is of degree 1. If it's of degree 2, you go up to here. So for as many degrees as you have, you can factor out your polynomial to fit this form. Now, what are these c's? What are these c's? These c's are equal to the zeros, or the roots, of your polynomial. So, let's say I told you you have a repeated root at -2. Well, then in that case, you would write your polynomial is equal to x plus 2 times x plus 2. So what we're saying here is that you have 2 roots. Both of your roots are equal to 2. Well, we have to subtract our roots from each of these factors, in each of these factors. So if your root's equal to -2, subtracting a negative, it's just going to give you a positive value. That's it. So we're subtracting the roots to find these linear factors. So when we find the roots using the quadratic formula, like we did for I and -I, well, we can use those to factor out our function, our polynomial. It's pretty nifty, actually. Now, having said that, because this obviously takes a little while, let's ask a slightly different question of this second example. How many solutions, how many roots will this second example have? Now, are they going to be real or complex? Well, in this second example, we've got 5x squared minus 8x. This is equal to 0. And to find out how many different solutions we're going to have, first thing we can look at is, well, this is degree 2, so we're going to have at most 2 answers. And the second thing we can look at is, well, because this is degree 2, we can apply the the discriminant. So because we can apply the discriminant, we need to know what A, B, and C are going to be for this polynomial. A in our polynomial is equal to 5. B is equal to -8. And C, well, there is no constant, so it's just 0. All right, cool. And our discriminant is equal to b squared minus 4ac. C is 0, so this sucker disappears, right? So what we've got then is our discriminant is equal to -8, that quantity squared, minus 4 times 5 times 0. Well, all of this is just going to be equal to 64. And the last time I checked, 64 is positive and greater than 0. So the solution to this will be 2 real solutions. And that's it. That's all I really have on discriminants. But let's keep chugging along. All right, so for this problem, we want to find the solution to our polynomial. Well, that means we're going to need to find the quadratic formula, or apply the quadratic formula, right? Because this is x squared, we can do that. Because we can only, again, we can only apply the quadratic formula to polynomials of degree 2. That's the only time. That's definitely degree 2. All right. So it's probably going to be nice to know what A, B, and C are. A, in this case, is equal to 1, right? B is equal to 2, and C is also equal to 2. Well, we're going to have to find it anyhow, so why don't we go ahead and just calculate the discriminant? I know I said literally not even a second ago that we were going to be done with the discriminant. I lied, I'm sorry. Let's go ahead and find it. We're going to need it anyhow, right? So the discriminant is going to be b squared minus 4ac. This is going to be then 2 squared, like me. I'm squared. Whatever. Anyhow, so the discriminant is going to be 2 squared minus 4 times 2 times 2. Yes, I'm laughing at my own joke. And I made a typo. I just realized I made a typo. Where's my typo? This is supposed to be A, right? It happens. We all make mistakes. Let's fix that really quick. So the discriminant is equal to 2 squared. Damn it, I did it again. 2 squared minus 4 times 1 times 2. All right. So that means then our discriminant is equal to 4 minus 8, which is equal to negative 4. Last I checked, negative 4 is less than 0. So we know that we're going to have 2 complex solutions to this, right? Automatically, this tells us we're going to have 2 complex solutions. So let's do the rest of the math. Now we know x is equal to negative b plus or minus square root of b squared minus 4ac all divided by 2a. Well, we know 4ac, b squared minus 4ac is equal to negative 4. So this is going to be x equal to negative b is 2 plus or minus the square root of negative 4 divided by 2 times a is 1. So all of this is going to come out to be negative 2 plus or minus I times 2 all divided by 2. Well, we can reduce this down to just negative 2, my mistake, to negative 1 plus or minus I. So this tells us then that x is equal to -1 minus I, or -1 plus I. Now that's interesting, isn't it? I think it's interesting. Ha ha ha, to whoever was like, no. What's cool about this is that these come out to be complex conjugates. Huh. So, is that always the case? If we're going to have complex solutions to a polynomial, do we always get them in pairs, and are they always going to be complex conjugates? Yes and yes. The discriminant tells us that they're always going to come in pairs. And if we look at what's happening, we can see that they're always going to be complex conjugates. Because what happens underneath the radical doesn't change, right? So we're just adding or subtracting it. So if this is going to be an imaginary value, any real value plus or minus an imaginary value is always going to be the real value plus the imaginary value, or the real value minus. It's always going to be those complex numbers. Well, they happen to be flipped. So that means it has to come out to be a complex conjugate every time. In other words, if you get a solution for one of these, you automatically have the other one. Let's say you were able to look at this equation and be like, oh yeah, obviously -1 minus I is an answer. Well, then you know that -1 plus I also has to be an answer. Not just that, now you know that you can factor this out. Now you know that x squared plus 2x plus 2 is equal to, by linear factorization theorem, x minus c1 times x minus c2. Well, we can imagine a case, or we can imagine c1 being equal to -1 minus I, because it's one of our zeros, right? And these have to be the roots or zeros of our polynomial. So this means one of these has to be x minus -1 minus I, and the other one has to be x minus -1 plus I, which we can now rewrite as x plus 1 plus I times x plus 1 minus I. And again, that's because by linear factorization theorem, C1 and C2 have to be zeros of our polynomial. And that's what the quadratic formula solves for. Cool. Let's keep plugging away. All right. So in this example, we're trying to find a polynomial that has these zeros and is equal to 200 whenever x is equal to 0. Oh boy, this is gonna suck, right? No, not really. Not at all, actually. It's gonna be pretty quick. So, the first thing we know is that when x is equal to 2, or I5, imaginary 5, whenever it's equal to those, our polynomial is equal to 0. Well, we know something from earlier in the lecture. complex zeros always come in pairs, and they come in complex conjugate pairs. So if I5, if imaginary 5 is a 0, negative imaginary 5 must also be a 0. So we know this right away. All right, so because I5 is a 0, so is negative I5. All right. So together this tells us that our zeros, or roots, are 2, 2, I5, and negative I5. And from the linear factorization theorem, we know that our polynomial can be rewritten as some number a times x minus 2 times x minus 2 times x minus imaginary 5 times x plus imaginary 5. Now where does this a come from? Well, this a is just a constant that we have to throw in just in case. We don't necessarily know that polynomial is exactly that, right? Because if this whole thing is 0, doesn't matter, a times it, it's going to be 0, right? Like, that's a gimme. So, for scaling, we have to have it in there. Okay, well, this next part tells us that whenever x is equal to 0, our entire polynomial is equal to 200. This part's going to let us solve for a. Now, what this means then, so we're just going to put 0 in for each of these. We're going to find that a times 0 minus 2 times 0 minus 2 times 0 minus imaginary 5 times 0 plus imaginary 5 is all equal to 200. Well, we can simplify this a little bit and rewrite it as a is equal, or a times negative 2 times negative 2 times negative imaginary 5 times imaginary 5 these two are going to give us positive 4. So we're going to have a times 4. These two, when we multiply them together, will give us 25. Which is equal to a times 100 what we have now is that a times 100 is equal to 200, or a is equal to 2. So we can work this backwards. We can use a little bit of information, what our zeros are and what one solution is, and find out what our polynomial is. Because now what we got is our polynomial is equal to 2 times x minus 2 times x minus 2 times x minus I times 5 times x plus I5. This is our polynomial. That's what we just found. And we found it by working backwards. Cool. It's pretty convenient, actually, when you think about it. This is another way of, like I said, solving for these polynomials, finding out what they are. Let's keep moving on. All right, so I keep talking about complex numbers. We've been talking about them for a little bit now. But how do we graph them? Like, if I wanted to graph either one of these complex numbers, how would I graph them? Well, first thing we need to know is how the complex plane works. The x-axis represents your real numbers, and the y-axis, well, it's your imaginary numbers. So having said that, if I wanted to graph -3 plus imaginary 4, well then, the x-axis, like I said, represents the real numbers. We want to go 3 units over. And the y-axis represents our imaginary numbers, so we want to go up 4 units. So this first complex number would be somewhere right about here. -3, 4. Huh. And the second complex number, 5, in the real axis, so it's going to be over here somewhere, right? Minus imaginary, just the imaginary number, so minus I. Means we're going to go down 1 unit. It's going to be around here-ish. It's 5, 1. This is how we graph complex numbers. We treat the real part like the x component, and we treat the imaginary part like the y component. It's graphed exactly the same way from there. Cool. So let's look into this a little bit more. Let's dig in. All right, so typically in math, when talking about complex numbers, mathematicians usually like to represent them with a z. I don't know why. I have no clue why. But we like to use z to represent complex numbers. And if we wanted to take the absolute value of a complex number, we would take the square root of a squared plus b squared. So knowing this, to really quickly answer this question, we want to graph the complex number 4 minus imaginary 3, and we want to find the absolute value. So let's go ahead and graph it. That'll be pretty quick. We want to go over 4 units in the x direction, or in the real direction, right? And then we want to go down 3 units. So it's about here-ish. 4 comma -3. All right. Now to find the absolute value of it, we're going to say absolute value of 4 minus I3. This whole thing is equal to the square root of 4 squared plus -3 squared. Well, this is going to be equal to the square root of 16 plus 9, which is the square root of 25, or just 5. So we can come over here and say that the absolute value of z, which is equal to the absolute value of 4 minus imaginary 3, this thing comes out to be 5. Well, hold on, wait a second. Let's look at this. Let's see this for a second, because I think I see something. looking at this, if instead of the imaginary plane, we considered this to be just the XY axis, right? The traditional real plane. Wouldn't this just give us the distance from the origin? Yeah, right? Like, that's how far we are from the origin. Well, if that's the case, does that mean that this point is 5 units away? That what the absolute value of a complex number is the distance that complex number is from the origin? Yeah, that's exactly what it is. The absolute value of a complex number tells you how far it is away from the origin. So hold up, wait, let's think about that again. Let's take another second to digest this. That means these things kind of are acting sort of like vectors. Yeah, they are. Complex numbers are vectors of sorts. So that means we're going to be able to do a lot of the same things with complex numbers we were able to do with vectors, like turn them into unit vectors. Except here it'll be some number, some imaginary value or some complex value times a constant. But it'll come out to be the same thing, right? Like, we'll be able to normalize our complex numbers in a similar way. We'll be able to write them in terms of sine and cosine. We'll be able to do all sorts of similar things with complex numbers that we were able to do with vectors. Having said that, I will let you all go. If you all have any questions, by all means, shoot me an email. Have a good one, everyone. Enjoy your break. # bring me some turkey.